Let's briefly discuss one or two things about decision trees. The first one is, how can a decision tree model a linear effect? Here's a linear effect, price, and living area. Imagine the price increases with living area in a perfectly linear way. That's not bad, that's almost a straight line. Right, living area 100, 200, 300, all the way up to, I don't know, 10,000. You tell me, what is the first decision we should make? How are we going to create a decision tree which uses the living area variable to capture this kind of straight line over here? Well, we have to take some point on living area and we have to split. So let's say we split over there. Okay, we have all the houses less than, what might that be, 5,000 square foot. How are we going to predict the price of all these houses at the bottom? The only thing we can do is to predict their average price, which is that price over there. And how are we going to predict the houses at the top? Again, we have to predict their average price. Good, we've made one split. What can the next split be? Well, I guess we have to split at 2,500. So we'll make another split over here. And this time, again, the houses less than 2,500 will predict at their average price. More than 2,500 will predict at their average price. What do we do next? Well, we can do the same for the larger houses. Make another split in our decision tree at 7,500. Something like that. If we want to have separate predictions all the way up and down this line, the only way to do it is to split again and again and again until we have a split for every different value of living area. And what does such a decision tree look like? Here is what such a decision tree looks like. It's insanely stupid. If you think about it, all a linear model would have had to do in this particular case would be to write price, sale price equals beta 1 times area. Just one parameter. And here you've got loads of different leaves. Another problem is that one parameter on sale price is actually estimated using all of the data, but each of these leaves at the bottom is only estimated using the data that falls into that leaf. That means if there's any kind of noise in your data, you actually won't even pick up you actually won't even pick up the linear effect properly. Let's talk also now about categorical variables, especially high-value categorical variables. Can you imagine what would happen if you put postcode down a decision tree? It's going to split. It will certainly always split because each postcode splits the data into very small pieces. And if you split data into very small pieces, you're bound to find one postcode which has cheaper prices and all the other postcodes have more expensive prices. It doesn't necessarily mean it's really true that that postcode has cheaper houses. It can just mean that by a fluke, the small number of houses that fall into that postcode are cheaper than average. So what will happen is, again, your tree will split on postcode again and again and again. Now, at least this particular time we knew that categorical variables gave us the same problem in linear models, so this is not a way in which trees are worse than the linear models, but we need to find a way of dealing with it. And actually the way to deal with categorical variables in decision trees is probably exactly the same way that we talked about for high cardinality categorical variables at the end of week 4. For example, target value encoding. Here is a tree which I fed a high cardinality categorical variable into it. It carries on going and going, and it's really horrible. I can't even show you the whole thing. So do not stick HCCVs into trees. Unless, of course, the tree-based method which you are using actually deals with it for you. And one of them, which we are hopefully going to see in the not too distant future, is CatBoost, which will actually deal with HCCVs for you, which is really nice. There are other kinds of tree and some of them are really nice, and if we had time it would be great to look into them. C 5.0, it can give you a set of rules at the end which are really useful for marketing campaigns, for example. C tree, which is a different way of splitting. C tree takes a long time to grow, but it does check that the splits are statistically significant before it makes the splits.